area of research that I was studying these has an emerging area in the last few years. Although company were already thinking around with pretty much this lost interest where getting involved and have been to provide some chemical reaction, but certainly has not been the mainstream approach as the conversions recent history at least. The idea is basically that we take a ball mill or similar device, we induce balloons, and we put it to create very interesting reactive environments by a number of different phenomena. Importantly, this is an approach that we use to program solids, including solids, fuel cells, with solid catalysts, and thus some those two challenges that I make on. So first, it's one on the right violence. For number, I will show one example from the Schultz group where they have some strong evidence that students are being activated, rearrange services and kits and the rearranged form of that kind of standard activity in the relaxed annealed material. We will also talk about costs, but it's basically the mechanic energies converted to heat polymers. I will not have time to cover trap electric effects, but that's mechanically induced charge separation, which in certain cases can absolutely play a role, especially if you have feedstock or catalyst that support as an electric insulator. In organic reactions, there's strength bonds when molecules are being spotted. The orbitals that make up chemical bonds no longer overlap in the most effective way, and that can dramatically lower activation energies they're occurring. And then, of course, as I mentioned in the previous slide already, we can have solid mixing and thus create new surface interactions that will be difficult to introduce with any other means. Now, the application of mechanical energy by no means precludes me from also using other energy sources. We have milling vessels that we can heat, which in some cases helps the reaction. In another case, in some other cases, we do this to get products out because if we mill temperature, the 50 degrees that we reach to punch is from the olive oil. So what we reaction we need that for this process. So the first part of my talk, I'm going to go through some of the fundamentals, and then we will talk about specific applications. So for the rearrangement of surfaces, there's this work that got here published in this one. Actually, was my point. They had a modified milling vessel that flow CO and oxygen through the vessel. They mill side. And I see that the activity and the conversion carbon monoxide, carbon dioxide increases with increasing milling time after some reduction period here. And they reach a very active form of that catalyst after about 5 minutes. And then it reaches a steady state. And they turn off the mill, they lose activity. So you do need the continuous energy supply. So the conversion of mechanical energy to heat seems to play a role as well. But this long induction period and increasing activity shows you that there is some rearrangement of a non-equilibrium surface that gives rise to this unique catalytic activity in the reference. We may move into details on these mechanical hotspots. And for that, we did a study of a very well model system, where ultimately the application of the module position of calcium carbonate. To understand the process, we first want to know what exactly are the trajectories of the milling laws, what are the complexities. And we built a plexiglass twin of our stainless steel milling vessel, and then filmed that and developed a program that allows us to track that the position of that on every frame of the movie, thus the speed, determine the kinetic energy, So whenever the kinetic energy changes, there's an energy transfer to the environment, and that's the energy that we work with. We then developed a three-step model. We assessed the collision, including the information elasticity of the wall. We did other experiments to determine how much how much so by the impact surface. We measured the heat transfer rates of the bed of calcium carbonate as our model system to model the rate at which the mechanically induced phosphor will decay. And once you have all of this information, you can treat every one of these collisions as a transient batch reactor that exists realistically for a fraction a second. That starts with the maximum hotspot temperature after the impact, and then the temperature decays as the heat is dissipated to the environment. And so we validated the system for calcium carbonate decomposition, calcium oxide, and CO2, mostly because this was a convenient reaction to the fast analytics for million vessels worldwide. We had a burning stream that went in, and we had a mass spectrometer measurement train of CO2 to the effluent. And when you do that, measure the rate CO2 formation, and you can calculate the temperature that you which have to reach in you produce CO2 and then from heating 1.5 calcium carbonate. So these apparent temperatures fall into the range from 784 to 854 Kelvin, depending on the milling frequency. But really, the temperature at the most needs to be hotter because most of my calcium carbonate will be at slightly above temperature for most of the time, and the reaction is much more localized. So that's when we applied the model. We went back and calculated how much these impacted volumes have to explain CO2 release at the rate that we observe it. And it's slightly above 11 Kelvin. They exist for that very high temperature for a few milliseconds. The decay occurs on the order of tens to hundreds of milliseconds. The impact of volume for that particular stay again. There's also transformation materials. So here's some actual reference. It's outbeing for and this many for 11 hours at different frequencies. Let's see that originally we had particles in the order of about 13 nanometers, and they are both fractured and sintered. And these two processes of breaking them into smaller pieces and sintering the equilibrate, in this case, this led to similar particles of process. The other transformation we observed is that the calcite, that's the normal polymers that calcium carbonate will be in. You look at the thermodynamic fixed diagram for calcium carbonate, you will find that we need 20,000 atmospheres of for everything to become thermodynamically equivalent base. So while mechanical impact and pressure in a steady-state system might not be directly parallel, let's do something about the conditions that this material will experience. So I hope that this gave us a bit of feeling for the conditions that we can create, and I want to transition a number of studies for the use ornaments as mechanical reactors to very specific conditions. The first study I want to talk about is synthesis. In this case, again, we have modified milling vessel, we have master controls for hydrogen that are continuously applied to the vessel, and then we can detect the formed ammonia by only what's in the middle. In this case, ammonia dissolved from catalysts in vessels at low temperatures is actually a non-trivial task. So in bigger study, we start vessel. And we can look at what happens to the catalyst. We used titanium as a pre-catalyst and nitride as action catalyst, because at the time we were funded, we started with the metal, we converted it into the nitride in situ, because at that point we can make a credible argument the night is really long. It's the usual. We have very nice president at any level beginning. An hour and a half beginning, we start seeing the fraction that are restricted to titanium nitride. After 6 hours of milling, this become a far dominant function of the middle still is first, but it's small. Now, right now, in the function are milling on a material. With that, looks sort of exhaust and things and upwards. And we can see in the exhaust in the variables that the material here in the front. It's really obvious. This peak here, that's also characteristic. You have characteristic even than any foil for the metal, and then it's left when the conversion so the fusion seems to be nearly complete. We actually achieve a certain titanium to nitrogen ratio that is rich in nitrogen, and so that tells you about some active nitrogen nitrate species on the surface, and you can have that. We did various building experiments. Some where we started with the titanium nitride sample that was Persian, others that are blue on this slide with metal, and finally linked with the induction period we observed when we started with the metal. That needs to be incorporated when we mill hydrogen and we are milling endless big hours. This is true. You continue in around nitrogen experience that already some confidence that everything is getting distance. After the third bit here, then we repeat that now. And we start with the metal. 6 hours, the yield is about 20% compared to the nitride, and then you can do the conversion of metal to base before you can realistically use that system. The activity keeps increasing quite notably after that. So when we go from 6 to 9 hours of milling, we double. And when we go from 9 to 12 hours of milling, is another factor of 2.5. So as we continue, we are making a more and more active catalytic material that allows us to produce additional power. So then we did a couple of thermal reference reactions. We did temperature programmed reduction of titanium nitride that we produced. We saw that under thermal conditions, ammonia synthesis starts at about 600 degrees. We also assessed the thermodynamics, and we found that the more fraction of ammonia that we have at the site of production is immediately thermodynamically feasible below 1. Now, how can both of this be true at the same time? And this comes back to the transient nature of the active sites that we generate. So what happens in this process altogether is we have titanium metal that is gradually converted to the nitride during milling and nitrogen library. And once this is found enough, find out, we make an active catalyst. And when we impact that, we can create an environment, can rationalize it as a hotspot, although I won't rule out distorting of these environments as well. And that allows us to activate N2 under very energetic conditions. You make excess nitride. And this excess nitride will relax thermally over just probably 100 to a few hundred milliseconds. And during the relaxation, it passes through a regime where homogenization of the nitride to ammonia is both thermodynamically and feasible before it reaches its resting state and slightly above temperature. So it's in certain ways comparable to chemically looping, but without the inertia of having to heat cool the entire reactor, the inertia associated with that. All right, let me switch gears and talk about processing of solids for most of the rest of my talk. And one application that we found very attractive for mechanochemistry is plastics recycling. So you have very recalcitrant solid materials that with the conditions that maintain, you can put in contact with solid catalysts. I will start talking about PET, polyethylene terephthalate. Because they have quite a bit of more hydrolyzed, alkalized, and glycolize it. Typically, you're looking at processes at elevated temperature and often a few hours time to reach conversion. And so we turned to a process where we bonded PET with sodium hydroxide, with the products being disodium terephthalate and ethylene glycol. When you look at the kinetics of this reaction, we form a monomer at about a constant rate for about 12.5 minutes. And then we have a rapid acceleration of our rate by a factor of 3.5, and the rest, which happens very quickly. Now, this transition happens at the same time as our mixture of powders is converted to waxy phase that is coating the milling rod. And so that impacting this waxy phase is much more efficient than it was to impact a random powder mixture. At this point, we don't know exactly whether this is a stochastic argument that the reactant that coats itself around the milling wall that provides the energy is just a very effective way of chemical collision to impacting the flux of it. In fact, we didn't have steam collisions anymore at that point. But there could also be other reasons because this wax will flatten the wall collision. We will distribute the energy over a larger area and maybe that as well. When we looked at the residual polymer by gel permeation chromatography, we see that the residue doesn't change much. We have a little bit of mechanical cleavage of very large chains, but the maximum cross size distribution stays remarkably constant. So this is evidence for the impact phase tends to be converted entirely. And if it's not impacted yet, then you have residual polymer, but it looks very much like the original polymer that we used for this process. We further looked in kinetics by varying the energy input by changing both the material of the wall and the milling frequency. So in this case, we think that the surface of the wall is relatively uninfluential for this reaction. So it really all comes down to the mass of all of the same size. When we go from stainless steel as the standard material to tungsten carbide, we roughly double the mass of the wall. They become significantly faster. We reach complete conversion in 7 minutes. And when we go to a wall that has the density, because it's made of aluminum oxide, we found significantly slower. Similar observations can be made with the milling frequency because ultimately the milling frequency is proportional to the number of rings. And the milling frequency squared is proportional to the kinetic energy often. And unsurprisingly, far more middle, the faster conversion curve, and this scales quite nicely with the kinetic energy descriptor for the rate at which this reaction occurs. So basically, it's that we have a situation where the fundamentals of PET in this case. And what's moving the reaction is the creation of these big areas where we force them into each other. And once we do create these environments, the reaction seems to be relatively fast and lead to complete depolymerization of those mixed environments. And statistically, that can be described as a shrinking foam wall, while physically, what's happening is much different. So we went on, we wanted to understand these individual events in more detail. So some work that we did this was to understand the thermal hotspot. And Jacob Nittens in the audience here, that's a nice problem to build pieces of steel back to back. And we in this case on a PET film that we call sodium hydroxide layer. And we can measure what happens. So you have to bear with me for 6 seconds until you see the thermal map of the impact on the right. So we see there is an event. In this case, our temperature went from about 140 degrees C. It's not nearly as the hotspot for calcium carbonate decomposition because PET is a much more plastic material that absorbs that have a softer condition. The rate of decay was similar to this about 300 milliseconds. And then after that, the energy was dissipated. We also looked at the crater that is created by this event, and this is something that feedback did recently. So the see afterwards is not quite 3 millimeters. And within P measures these red boxes that are 37 items. And the round spectrum on DBT has 3 characteristic peaks that disappear when polarization occurs. And this allows us to measure the conversion at each of these spots. And we see that we go from about 3 to 4% conversion right here at the edge of the crater to about 25% conversion in the. So we're looking forward to understanding this in a lot more detail. What this would allow us is join forces with my colleague Pani Kumara, does discrete element thing. We have a paper that we just did with them. We filled the ball mill with on sugar paper. This is its tools present, similar velocity reversed, sensitivity, also host events that will be steel balls up in each other. And we validated this model systems balls, but this will not be the end. So Fanny is working on a model. She's got with me here that has 7,000 centimeters. And at this point, we will be able to develop statistical models that might be akin to a Boltzmann distribution and start assessing the acid. So we transition to a couple of other groups. We also work with polyethylene, which would not activate easily because I don't think it's the bonds. It's the making point of it. So in this case, with my list and hydrogen oxide as an oxidant. And this allows us to randomly oxidize some of the carbon atoms in polyethylene. And once you have done that, you've created a point of weakness where you can break this chain into pieces. The chain ends are oxygenates, but we also do see some decarbonylation activity. So some fraction of polyethylene will be sacrificed as CO2, but that is relatively minor. If we're able to show that we have increased abundance of electrons in particular in this polymer, and when we GPC analysis, we find we define distribution where the small molecular weight fraction is in the range of 6 to 30 carbon atoms. So this is a range in the range of proteins. And if you take the integrals, which we see for base value, which we should be, but we get to approximately 38% yield in this case from a feeding process that is far from being optimized. So with longer, many times more effective catalysts, tailored conditions, I think we can take this much further. We also did some work with polystyrene. Some of you may have been able to listen to George Cheng's lecture yesterday. Polystyrene is an interesting polymer because it is known that we can purify this to the polymer at a sealing temperature of 400 degrees at unzips, and can actually make styrene with relatively energies. When we want styrene, this is really interesting. Well, for 2.5 hours, we kept making styrene monomer in the ball mill, but then it collapsed on us and we lost our product. So this is a radical depolymerization process. And so we thought that the problem is probably that we create radical deposits and too much of polymerization there in the ball mill. Then some repolymerization. How can we prevent that? Well, we have to continuously remove the product, and we do that by implementing stream in the process. And collecting this idea that we very often in money spots here where the furniture has used the top partners and slightly accumulated in the track the department. We stay on this constant trajectory and we keep making objects approximately constant yield. So once you have solved that, this process can keep making an extended time. So this is the one where we'll talk about manual conversion specifically on 15 years, various plots that convert lignin to phenol. Again, phenol could be a platform molecule in future iron finding. So this three-step process. We need to depolymerize the lignin to monomers. Once we have this mixture of monomers, we need to do two things. We need to remove one by one oxygen atom, which is something that we have worked on and not talked about today in this time. And then we need to remove the unqualified chain monomers in the credit. Those last two operations you can do in principle in either order, and practicality will dictate which one is preferable. And I'll just highlight the aspects of this other project here where mechanochemistry and mechanocatalysis play. It did the depolymerization. In fact, that was the first project in this space where we wanted to find a way how we could convert lignin without having the separation problems at the end. To get the lignin monomers and catalysts out of the solution with many different things at the same time. When we formed organosolved lignin by itself, it was checked. When we added sodium hydroxide as a base catalyst reagent, we see depolymerization. Most of it happens in the first 20 minutes. And then we stabilize at 2.5 monomers per product molecule. When we added methanol as well, things become much faster. So most of our depolymerization occurs in the first 5 minutes. And most products have 1.5 billion loss of monolignons. So what does the methanol do? It's probably not reactant, but rather a scavenger of the products that we're making. Lignin chemistry is notorious for having repolymerization of radical products. And the methanol is actually good as a hydrogen donor that can stabilize these radical reactions that often lead to more repulsed or repellent than original thing. So thus we are able to stabilize these small molecular products, which presumably true in the absence of methanol, but they just react really nicely. We also went into different chemistry. We were interested in what can we do with hydrogen as more effective and cheaper scavenger on a per mole basis if we can make it work. For this case, again, we turned to flow through Ormel and we started working with benzophenol exides in one component and nickel catalyst on and then and still these as all products. When the phenol resides in mineral process for an extended period of time, you see some green hydrogenation, although that is slower than the chemistry. And we see some minor reaction products, but none of those exceeded yields percent. We see that the volume readily forms as per the milling vessels, whose volume in this case was collected from the track downstream, whereas the phenol tends to remain. We also see that the phenol yields, even when you add the contributors and students, the toluene from the other half molecule, and the chemisorption of phenolates, and even acid sites that binding catalyst had in the first place, but also fraction sites that you make it during this mechanical process have a high affinity to chemisorpting oxygenates. So, we can what needs. So this worked reasonably well with nickel. And then Aaron Phillips, who will talk about this later this afternoon, started looking at other catalysts. And we found that we saw water frequency by a factor of 300 when we go from nickel to palladium. So that's impressive. We know that palladium is a good hydrogenation catalyst, but this rate increase exceeded what you would expect purely on the surface chemical argument. Now, the major difference that we propose here is the fact that palladium can very easily bind hydrogen as bulk items. So hydrogen can penetrate into palladium metal and thus be stored. We see evidence for that in cells. The peak of our palladium metal is something to longer distances out of space. And this is characteristic for the incorporation of hydrogen fluoride. So now once you have created this pool of solid hydrogen, if you will, you don't have hydrogen escaping from the point of collision anymore because you can go on the surface and the rate slows and pressure, you can slow escape. By binding hydrogen in the metal, we eliminated this escape. Right. This chemistry that particle thus is a lot efficient. So the last study that I want to highlight is one where arguably we did conventional fluorine chemistry, but we used mechanochemistry as a synthesis technique. In this case, we wanted to remove the alkyl side chains from these lignin monomers that we have made in those depolymerization reactions. And this is a C-line catalyzed cracking reactions. There were also problems with chemisorphed phenolates, which can reasonably counteract by feeding water during the process. When we did that, we still had issues with coping. These molecules depositing and preventing access to the force of the C-line and ultimately the cracking reaction. To mitigate that, we turned to mechanochemistry as ways of laminating the near-C-line materials. We have an MCM22 that silver produced units. Then we put that to shear these layers against each other, separate them from each other, and create a hierarchical core network with a massive force that can act as diffusional highways. This is very similar to how the cores where they adding Q2 mechanical means that also that makes these massive forces more efficient access towards even when you have submarine position. When we did that, and we used that for cracking for phenol, we hear that the conversion is lower with the woman material, still much higher than the chemically delaminated material that we prepared. But the mesopores materials or the chemical materials, we have to make them slower rates. We computed the rate constants for the activation by in the rate constants 10 months. We see that after about 4.5 hours in the stream, the conversion with the material that we prepared by mechanochemically delaminated steel actions becomes the more active residual activity. All right, so with that, I would like to draw a few conclusions. I hope that I was able to convince you that collisions potentially similar devices with reactive with materials we can get to about 8 degrees for very short periods of time. There are processes where that is exactly what. And I see there's a lot of potential for processing solid systems. So I have two last slides. The most important one in this talk is, of course, looking at the domain use for. There's a long list of students and bookstocks that I'm on that I should think on every tracker was really the instrumental grant in taking this project that one was working on one that that is becoming a defining point right now. We have 6 postdocs working on mechanochemistry at this point. And a lot of collaborators contributed different skills that I don't have time to mention. And while we take questions, I will put one slide here to have a consideration. Thank you.
Indeed, it's very interesting chemistry. I have a couple of questions actually. One is related to the steady state behavior, especially of the gas and solid reactor. One would expect that in due time, the catalyst actually is reduced to fine particles, and then this transformation of mechanical energy into thermal energy becomes less efficient. So you sustain in time this phenomena.
So such violence, I think we have both strength, but also still making very obvious areas and design decisions. And so this money will find that delivery, this phenomenon that will be delivery process. But the company don't get infinite this. Then you are in this condition of works. You had the box checking the progress and what
now going of the project. In this case, I show C4 to C7, and usually that's is the light again styles with large enough difference between all species. Simulated the separation process using and I having that be a high purity outputs using the approach we proposed first to half the gas outside to fraction distillation or so practicing this slide. Yes, we can this kind of result for postdoc generated from real waste process then we can get high purity products from this technology. To conclude, I hope I convince you that combining pyrolysis and hydrogenation is can make a great upside in this plastics. And it's a very exciting technology for plastic recycling. We also change the physics. In this case, we can get different structures, molecules, thus elements. And we can use this elements to produce a wide range of atoms. With that, I would like to acknowledge my collaborator, Jaya, Jen Rizzo, Professor Victor Spala, Professor Carl Hennis, Professor Members, I also want funding from Leo Rizzo and support from Professor. With that, thank you for your attention, and I will have questions.
Discussion, please use the private or one sheet. Sure, go ahead.
Hey, I have a question for you. So the first one is why don't we control this 7 spot? Still, why? There's the only this. Can you like people question? I think one of the studying this problem is that on one side, I have one way is on the one, makes it not the same. Oh, I think I show you like I think the question is you ask whether I'm having this result in balance. It's brain so to see my for some poisons of harvest using it in her so that food has to be all complex has appliance. Yeah, it should. It's not like you don't have to see everyone else with money directly. Oh no, we don't see because this kind of nation occurred actually temperature and we don't because it's often we don't see anonymous exhaustions, for example, situations so such as
Time for one more question. As follows. Okay, now we'll have our next speaker come up and thank our speaker for the next talk is Suzanne Scott. She's our keynote speaker today.